Welcome to this lesson. Nice meeting you again. Hope you're doing well. So in this lesson, which is chapter 7 of the designing application, designing multi-agent system application. So in this lesson, we'll be looking at learning in agentic system. How do agents learn? Okay, how do they learn from their environments? How do they learn business use cases? How do they learn in design? So a comprehensive summary of how AI agents learn and improve over time through interaction and fine-tuning. So AI agents learn and improve. So of course, you know that when you are designing agentic system, for instance, you put these things into consideration. We have mathematics, which is what allow the agents to optimize, which is called optimization. So you must make sure the agentic system give its best, give accurate information. So you must put define the objective function and make sure it is maximized. And then you must also implement logic. So the agent must be able to know the difference between what is good and what is bad. It must not take bad for good. It must not take good for bad. And then a strategy, that's strategic thinking, which you can implement through reasoning and acting and planning. So these are very, very important when you are designing agent. And then the agent don't just start planning. It doesn't just start reasoning or acting. You have to teach it how to do so. Okay, so this is why learning is very, very important in agentic system design. So learn how agent improve through interaction or requires significant architectural design. So this is very, very important. And this is where many LLM developers and many agentic AI system miss it, because they do not properly design for how the agents should learn. So you can't just inject prompt into your agent and expect your agent to start behaving. If the LLM is not defined, is not designed properly, any misinformation coming from the LLM will also be transferred into the agent, even when you properly design your prompts. So learning must be properly designed into the architecture of the base model and the agentic system as well. So we have two types of learning: non-parametric learning, where the agent improve without changing model weight, and we have parametric learning, where the model itself is fine-tuned, it's fine-tuned by changing weights. So those are the type of learning we have. Non-parametric learning, so improving agent performance without retraining the foundational model. So how is this done? This can be done by using examples, by giving the examples or using practical example or real life example of what it should do, how it should do, or how to solve specific problem. This is like teaching, a robot how to walk, for instance, how to jump, how to wave to somebody, or how to, bend, and so on and so forth. So you give it an example of what to do. Then the non-parametric can also be achieved through memory. So of course we have said RAG database. So you can develop a RAG database where the LLM collects information and use it to augment whatever it has. And then it can be reflection based, where the agent has the ability to reflect on the surrounding environment and pick up information from its environment. Then we have the non-parametric exemplar learning. So here, learning from successful past examples to guide future task completion through few short prompting. So this is where the agent is able to learn from past examples, and then it carry past example to the current task or future task through few shot prompting. So we have few shot prompting, we have zero shot. So few shot is giving the agent one or more shots or one or more examples to enable it to perform a task. So few short examples means add coded example inside a prompt, and dynamic few short example means relevance example are retrieved from memory and vector database at runtime. So you can develop few short example into the prompt, giving example of how to do a particular task in the prompt, hard coded into the prompt, or this few short example can come from a third-party database, which is the RAG database, where information has been chunked and embedded and can be retrieved by using hybrid search, semantic and keyword-based search. Then reflection, a self-critic mechanism where the agent analyzes failure to improve strategy next time. So this is where agent is able to act automatically, just act and improve itself without learning from anything. So reflection allow an agent to critique itself after failure. So it's make it the agent itself or the LLM make a mistake, review the mistake, discover that it has made it discovered that there is a mistake or there is an error in its operation, and then it corrects itself and recover from the failure and then continues. So that is reflection. So what went wrong? So this is how the agent goes through what reflection operation. So it's first examine what went wrong. Sample body test providing context or explanation to support the facial headline. What strategy does he miss? Or what can he do differently next time? Agent perform action in sequence. So when it examine what went wrong, where it missed a particular step, and then it will rethink what can it do differently the next time, and then it's just develop a sequence of performing a particular task, and then it's log all the errors and the correction and the trials. Everything is logged into the memory of the agent, and then LLM reflects on the whole of this operation, and then the reflection is stored in the memory, and the agent will not make this mistake the next time. So it works for human being, so it also works for agentic system. So basic reflection setup. So you initialize a chat open AI model and define the core execution node for the agentic graph. So to set up reflection, you must first initialize the LLM, and then you must call a particular function to implement it. So reflection prompts are structured prompts designed to force the model to identify strategic mistake and devise a new plan. So we have a framing instruction. You can frame the instruction, that is, tell the model it failed and should generate a better strategy next time. Or you can use the original task, remind the model the actual goal. So if the agent keep generating wrong thing, just remind it the actual goal. Then it can recorrect or redirect itself. Then action observation history. So show what went wrong, and then you can then teach the agent how to do it right. So code generation, reflection, and update memory. So logic of processing trial logs and persistent strategic reflection into the agent memory. So you can implement this function, generate reflection query, update memory, important idea. So you can go through this flow. Fail trial, when there is a failed trial, the agent reflects, and then it stores reflection in the memory, and then next time it performs better. So land graph reflection mode. So compiling the agent workflow and executing the reflection cycle within a state graph. So for land graph, it implements reflection in this pattern. In its state graph, add reflection mode, edges from start, compile an info graph, update memory logs. So this is the flow of land graph, which you can also implement into your model. So experiential learning, extracting generalization insight from multiple experiences to improve performance across diverse tasks. So for experiential learning, you can design for the following: added, edited, promoted, demoted, and removed. So all this can be put in. Then reflection comparison, a comparison of learning scope, storage, optimization goes between two methods: reflection, experiential learning. So learn from one field attempt, that's experiential learning, learn across many experience. So for reflection, is store reflections, and experiential learning store reusable insights. So reflection improve retrieve behavior, experiential learning improve general policy. Good reflection is actually good for task level correction, and experiential learning is good for cross-track task improvement. Insight agent. So this is introducing agent architecture design to generate and manage an internal learning states. So we have list a minute. So insights, newly generated insight, promoted insight, useful insight, demoted insight, so less useful insight. So these are like insight agent functions for managing the prompts of the agent. So inside agent setup, how do you set it inside agent? This is defining the class structure and internal memory list for the inside agent system. So you can use this function self.insight to define, and self.promoted insight for promoted insight, and self.demoted insight to define demoted insight. So generate insight. So workflow from raw observation into actionable insight using LLM-driven or graph mode. So you can design the agent to generate insight the following way. Agent send message to LLM, then LLM build state graph, LLM invoke the graph, generated insight, sort message, and then the example observation is then exposed. So traffic rose 15%, but bounce rate jumped from 40% to 55%. Landing page quality or targeting may be weak. So insight operation, active management of the insight lifecycle, ensuring that only high value knowledge is prioritized. So you can use promotion, as we have explained, promotion, demotion, and editing to design the following. So code insight, promote insight, demote insight, and edit insight. So this can be used to design insight for the agent. And the following are the example. You can use it to simulate KPI reports, KPI target met. If not met, it is demoted. So these are example of designing insights. So set the KPI reports. So if the KPI target is met, the agent is promoted, or the insight or prompt is promoted. And if it is not met, if it doesn't meet the KPI, then it is demoted. So as it work in general human resources, can also work in agentic system design. Parametric learning and fine-tuning. So remember, we started with two types of learning, parametric and non-parametric. So this is the parametric learning, which is fine-tuning, which is learning from data set or from evaluation. So deep specialization across weights, adjustments, offering high power at high complexity. So look at the situation. Or you fine-tune an agent where you need domain specialization. That is, the model must understand company or domain jargons. You want the model to be consistently formatted. That is, model must always follow a strict template, company template. It must not reason outside the company's information or data. To an API calls, model must call particular tools accurately. High quality data. So fine-tuning needs many good examples. It needs highest quality data. That is why fine-tuning is very, very expensive, because the data must be very clean. A summary of major fine-tuning techniques categorized by their mechanism and target use cases. So we have example, method, how it works, best for. So supervised fine-tuning. Train a prompt and ideal response pair. How does it work? Structured output, classification model and function calling. Vision fine-tuning, that is, you train an image label pair. So this can be done through image. This is best for image classification and multimodal task. We have direct preference optimization, DPO. This is trained on good versus bad pairs, best for tone, style, summarization quality. And then we have reinforcement fine-tuning. So this is trained using graded reward, and this is best for complex reasoning and the high-stake domain. Large foundation model, improving performance on specialized high-value tasks using enterprise grade large models. So the first is cost. So require compute and training resources. For you to fine-tune, you need compute and training resources. Very, very important. Maintenance. Model need versioning and retraining continuously. Drifts. That's data drift. That is the effect of change in data sets. Domain changes can make model to become outdated. Overfitting. So where you need to do hyperparameter tuning as if you are training a foundation model. So poor data can make the model too narrow. So those are the prerequisites that you must take into consideration. So very, very important. The promise of small models. So this is where SLM shines. Okay. So advantages of deploying specialized small model for latency, cost, and edge application. So advantage and explanation. So you can see the advantage of small models over fine-tuning. Lower cost, cheaper training and inference. Faster iteration, easier to fine-tune repeatedly. Lower latency, go for real-time apps. Edge deployment, can run on devices or local systems, can even run on your laptop. Sustainability, uses less energy. So this is where instead of fine-tuning a larger model, you can just build a small model and then fine-tune it to achieve your goal. So supervised fine-tuning, SFT, teaching agent-specific behavior and structured output format by using a clean data set. So you can implement the following: when to call tools, how to format tools. These are specific fine-tuning. When to call tools, how to format tools, calls, how to pass argument, and how to produce structured output. So function calling fine-tuning. So how do you fine-tune function calling? User message, desired behavior. So what is the weather in Boston? Call the function get weather. So you can design a function to call weather. Imagine it's snowing in Boston. Do not call real weather API. Okay, so imagine, this is imagination. So this is not an instruction, it is just an imagination. So the LLM should not go and call weather API for an imagination, because imagination is not a fact. Then schema discipline for tool calling. So make sure you implement define the schema and validate the tool schema to ensure runtime reliability. So always define the schema for tools calling. Define the function name, define the argument name and data type, define the required field, structure, return the structure and validation rules. Okay. So SFT with LoRa. So you know, when you're fine-tuning, you can use these two models, LoRa and QLoRa. So fine-tune selected part of a model efficiently affordably. So LoRa is always preferred because it is cheaper. So pre-processing, that's tokenizing raw samples into prompt, tokenizing setup, building tokenizer with special token, quantization, that is implementing 4-bit quantization for memory efficiency, data set prep, prepare the data set, clean it, and make sure it is splitted for fine-tuning, and then run execution via supervised fine-tuning trainer, which is the LoRa. SFT pre-processing and tokenizer. So when defining converting conversation history to training format and managing special token, use this function: build or pre-process function, build tokenizer function, and implement special token, which facilitates separation of reasoning, dialogue, and tool calling. So SFT model and data set. So for the base model, build the model with 4-bit quantization and preparing the training data set. So you can use build model function defined like this. You can use load and pass data set raw defined with this function. So these are just some definition. So SFT training and function. The training configuration and execution loop for efficient LoRa-based supervised fine-tuning can use this function: output directory, gradient accumulation step, evaluation strategy, use epoch and define the epoch, BF16 set to true, maximum sequence length set to 1500, and packing set to true. So direct preference optimization, this is DPO, which means training model for prefer high quality response over low quality alternative. So the field that you should define, and there are many prompts, which are user request, choosing better response, and rejected worse response. Okay. So DPO setup, import, and model. So initializing the DPO training environment and loading the quantized base model. So import DPO trainer, DPO config function, import the DPO, set base SFT, CKPT, where you call your base model file 3, for example, Microsoft file 3. Then configure bit and bytes with this function. Set bit to true, and then set double quant 4 bits to true. Then you load the base casual LLM, base SFT, CKPT, device map set to auto, quantization set config set to BN. Then DPO, LoRa, and dataset. Configure the low rank adapter and landing preference data to help DEX optimization. So code init should be LoRa, PEFT, and database setup. And then we have the DPO training and config, where you set up your beta states. First one, DPO config, followed by DPO trainer. And then the verifiable reward will go this way: sample prompt, generate multiple completions, grade completions, and convert grade into reward. So if you are implementing this in Microsoft Foundry, those are the pattern that it will take. So a strategic summary of learning method, their resource cost, and ideal application. So these are the method, this is the changes model way, this is the cost and best use case. So exemplar learning, the course is slow and it is used for reusing successful example. Reflection, the course is low, it is used for learning from failed attempt. Experiential learning, low can be low to medium, used for general insight across tasks. We have SFT, supervised fine tuning, the course is medium or high. Okay, and it is structured output, used when you want structured output or tool calling. We have DPO, medium or high cost, used for high preference alignment. And you have reinforcement learning, uh, reinforcement learning fine tuning. The cost is very high, so used for optimizing, use when you want to optimize with measure. You can use it when you want optimization with measurable reward. So practical recommendation. The recommended path for implementing learning moving from simple prompts to complex fine-tuning is first, use prompt engineering. If prompt engineering doesn't work, use few short example, and then after few short example, you should use retrieval memory. So first of all, this is the agentic AI engineering design pattern. You should start with your base model, then use prompt engineering, few shot learning, or zero shot, few shot learning. If prompt engineering is not enough, then you move to RAG database. So if there is company information, you can ingest chunk and embed them into vector database, and then the LLM can retrieve information from the system. If that is enough, no need of fine tuning. But if RAG is not enough, then you can now go into fine tuning and so select one from the fine tuning or category. So final summary: non-parametric learning improve performance without changing model weights. So it includes exemplar learning, reflection, experiential learning, and these are practical and cheaper. Parametric learning changes model weights through fine-tuning, and it includes SFTDPO and reinforcement learning. These are powerful but require more data, more compute, and more maintenance, and more cost. So one line takeaway: use parametric learning first for fast, affordable agent improvement, and use fine-tuning only when your task is stable and it is highly demanded that you should use it. So guys, this is the end of this learning. Hope you have achieved something, and then if you like our videos, our channel, please do well to like and subscribe. Thank you.